And of course, as with everything, like with Lab 8, Phase 1 is always the trivial part. Anybody know Phase 1 of Lab 8? You'd like to think that. So, let's get started. We're close enough to there. So, I just wanted to give you my 2 bits that I know that we're coming to a raging close in the semester. We've got not very much time left. We've got Lab 8 left. We've got Lab 9 left. We've got maybe a couple of homework assignments. But I'm pushing you pretty hard, I know that. You know that particularly. I just hope you don't lose sight of the end here. Not necessarily the end of the semester, but the end as in the point. Because the stuff that you're getting out of this class will be directly relevant on job interviews that you'll be able to. You'll have an interview, you'll go to the interview, they'll ask you silly questions, and you'll look at them like they're from Mars, like, why are you asking me kindergarten stuff? Because they're going to ask you, what does static, volatile, and extern mean? You're going to know what the answer is. You know, I mean, relative to one of these midterms that I hand out, and any interview that you're going to go to that's going to be talking about embedded software is going to be very easy. You will be well prepared. That's part of the reason why I can't and don't slack off on what I put you guys through. So I know that I am putting you through the ringer. I know that I am making you work really, 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 really hard. And I hope that you feel that it's worth it. And I'm totally fine if you feel that it's totally not worth it right now. But I hope in 6 months you'll reflect back on the class and feel that it's worth it. I hope that you don't totally take it out on me in course evaluations, but that's okay. If you feel like you need to, it's okay. Unfortunately, one thing that I would like to tell you guys is we are going to be guinea pigs on a new type of course evaluation. So you're actually going to do 2 course evaluations for this class. I don't know that they're going to do the new course evaluation for the distance guys. So the guys down at Hill, maybe you guys are out of luck on the new one, unfortunately, or fortunately, depending on your perspective. So this new course evaluation is a lovely 40 questions. So I will not be in the room when you're filling it out. They actually make me fill out a questionnaire before they make you fill out the questionnaire. But they're figuring out whether or not they want to adopt this. So I would just hope that when you do the course evaluation, you'll evaluate the course, you'll evaluate the instructor. Don't evaluate the fact that the evaluation is horrible or boring or great or whatever. We'll also be filling out the traditional course evaluation on the same day. So this will happen a week from today. Okay? It'll take most of the class. So we'll have about 15 minutes or so of class that'll come in. And I'll be here for probably the first 15, 20 minutes, and then the rest of the time will be course evaluation. So just be prepared if you want to put in your 2 bits about the class. That'll be the time. But anyway, so I hope that you find the stuff relevant, and particularly when it comes to times of getting a job, I hope that you will find this stuff relevant. All right. So, questions, comments? How's the lab coming? Okay, I've got office hours this afternoon, and the lab is due next week. So today would be an ideal time for you to come and talk to me if you're stuck, or even if you're not stuck and you just want comments on things. Now, those of you who come to talk to me in my office have discovered, I'm pretty loose-lipped when it comes to giving away the answers. I know that doesn't necessarily help a whole bunch, but I'll tell you what to do, but you still got to do it. All right, so today we're going to finish talking about PCP semaphores. I'll probably go back and review a little bit more of the response time analysis for PCP semaphores. And then if time's left, we'll barrel on into the second phase of Lab 2, this PCP semaphore implementation. And I'm going to give you the whole code you're going to have to implement right here. That's phase 1. So then we'll have phase 2, which is implementing a software UART. Okay. So if you remember, I showed you an implementation of PCP semaphores last time where we queried a count and we had things that go on to block queues, but we debated whether or not we actually needed a count and whether actually we needed a block queue. And the point is there's a lot of optimization that can occur when you're implementing PCP semaphores if we recognize the fact that PCP semaphores are a little bit different in how they're actually used than a strong semaphore. So we've talked about the fact that with a PCP semaphore, we're implementing the immediate priority ceiling protocol. So when a process wants to grab a shared resource that's protected by a PCP semaphore, if it can successfully access that resource by grabbing its associated PCP semaphore, its dynamic priority gets elevated. Okay? It gets elevated to at least the level or bigger than the level, so it's higher priority or equal to the highest priority of any process that was going to compete for this resource. So by virtue of the fact that you win as soon as you get past the disable inside a PCP semaphore, you guarantee that nobody else will have high enough priority to get swapped in order to call PCP-P. So everybody else gets preempted. From the point that you successfully grab the semaphore, nobody else that wants this resource can ask for it. Okay? So this is the difference between a strong semaphore and a PCP semaphore. With a strong semaphore, somebody goes and grabs a strong semaphore, they start entering the critical section, somebody else comes along, maybe with higher priority than the process that owns the strong semaphore. That higher priority process becomes ready, and so he gets swapped in. The guy that owns the strong semaphore gets swapped out. He sits on the ready queue. He wants the CPU but doesn't get it enough because he's preempted because this other guy has higher priority. The higher priority process is free to go and ask for that resource, and he'll do a strong P on the resource, on the semaphore protecting the resource, and by virtue of the fact that the semaphore is not available, he gets put onto the block queue. Such a situation will never occur with a PCP semaphore. The reason why is because anybody with higher priority than the process that owns the PCP semaphore, well, what that means is that because by virtue of the fact that maybe this competing process has higher priority, higher static priority than the process that owns the PCP semaphore, that just simply implies that the ceiling priority of the PCP semaphore it's asking for is equal to or greater than this static priority of the higher priority process that wants the PCP semaphore. So when the higher priority process, when this low priority process asks for the PCP semaphore and gets it, its dynamic priority is elevated, and that just shoves this other guy out of the way. He can't ask for the PCP semaphore because he doesn't have enough high enough priority to get swapped in. So as soon as somebody owns the PCP semaphore, their priority gets elevated, they muscle everybody else out of the way, nobody else can even ask for the PCP semaphore that they're competing with, and he gets to run as soon as he gives up, as soon as he finishes his critical section, does a PCP-V, his dynamic priority gets lowered back down to his static priority and things proceed. So it's weird, but the following holds with a PCP semaphore. You can't not get it. Okay? That doesn't mean you are forced to not understand. That's not what I'm saying. When you ask for a PCP semaphore, there's no way for you to not get it. Okay? The reason why is because if you have high enough priority that you are the process with highest, if you have high enough priority to be running, that means you're swapped in. That means everybody else with higher priority doesn't want the CPU right now. They're either blocked or they're not ready, something else. They're not on the ready queue. Anybody with higher priority is not there, not available to run. You're the highest priority process that's currently ready to run. If you have high enough priority to ask for a PCP semaphore, you'll get it. And you're guaranteed to not be preempted by another process whose static priority is less than or equal to the ceiling priority of the PCP semaphore. It does not mean that you will not be preempted. You can still be preempted by somebody whose whose static priority is higher than the ceiling priority of the PCP semaphore. But that would mean that higher guy doesn't ask for this PCP semaphore, because the ceiling priority of the PCP semaphore is dictated by which processes compete for it. So, that's a lot of words, and it makes the head spin, and it's very hard for me to say the words, so I know it's hard for you guys to understand it. You're going to have to sit down and try to understand what's going on with the PCP semaphores. And I will explain it again in 14 different ways if I possibly can if you're confused about it. And this stuff gives students trouble every year. I don't know how to do it any better, so sorry, guys. PCP semaphore here, PCP-P. We pass a PCP sema, we disable the interrupt. Here's the comment. Once you're here, the calling process is guaranteed to own the semaphore. So if you have a high enough priority to ask for it, you're guaranteed to get it. You can't block on a PCP semaphore. All that happens is you make sure that you muscle everybody else out of the way. If a process competes for a particular PCP semaphore, if they have high enough priority to ask for it, they'll get it. And everybody else who also wants it, they won't be able to run by virtue of the fact that we elevate the dynamic priority of the process. So the first thing that we do is we set the priority of the running process equal to the semaphore's ceiling priority. Okay? How did we determine what the ceiling priority of the semaphore is? Well, beforehand, when we created all of our processes, when we wrote the code to create all the processes, we have to figure out which processes share which semaphores. Okay? So for a particular semaphore, we collect all the set of processes that share that PCP semaphore, and we figure out who's got the highest static priority amongst them. That highest priority of those processes that share this semaphore becomes the ceiling priority of that semaphore. Okay? So it's all based on who's competing for a particular semaphore. And this is set when the semaphore is created. Okay? Yeah, Mitch.
When does the process inherit that ceiling priority?
Right here. In the P. So the question is, when does the process that accesses the PCP semaphore inherit, when does its dynamic priority change? And that's exactly what this is. This is the inheritance process. Okay? So process running, arrow priority, this field represents the dynamic priority of the process, or in other words, the priority that the scheduler looks at to make scheduling decisions. Okay? We set the priority of the running process, and it's the process that's calling V, or calling P. We set its priority equal to the ceiling priority. Now, because of the fact we have to make scheduling decisions, and this is assuming that we're having the table-based scheduler, and the table-based scheduler has got all these priorities marked inside its internal tables, and when the scheduler goes and does a lookup and it says, who's the highest priority ready process, it'll access the tables and get out a number and say, this is the priority of the highest priority process that's ready, and it'll drop that into an array to get the pointer to the process that's ready. We have two tables, and I've mildly renamed the tables. We'll call this DIN processes or DYNE processes, dynamic processes. This is an array of all of your processes that you could create. So this is an array of 64 slots. Each slot is a pointer to a process. It is indexed by dynamic priority. We have another array that we index by static priority. The contents of the static priority indexed array won't change unless you create a process. The contents of the dynamic processes array, this is what we were calling all processes last time. The other one's called hold processes. So dynamic processes, this just reemphasizes the fact that this array is indexed by dynamic priority. So we say the dynamic processes array at the slot of the ceiling priority of the PCP semaphore, we point that pointer at what process running points to. So inside this array, we just say, okay, the pointer at the ceiling priority of the semaphore, that points to the current running process. Okay? So here we set the current running process's priority to the ceiling priority. We set the entry in the dynamic processes array at the ceiling priority the running process. And now we just mark the entry in our ready queue to state that the running process's dynamic priority is ready. Basically what we're doing is we insert process running into the ready queue. Now, if you recall, I've mentioned a few times how you've got to decide whether or not your running process is in your ready queue or not. And you can do it both ways. This is the design decision that I made to have my running process in the ready queue. So in this fashion, what I'm doing is I'm making sure that the running process is always in the ready queue, so that way whenever I query my table, it'll tell me what's the highest priority ready process, and I just compare that to see if that's the running process or not. Some students have chosen in the past to implement their system such that the running process is not in the ready queue. And if that's the case, you would not do this insert inside PCPP. Okay? All right. A consequence of this decision that I made of having the running process in the ready queue imposed a slight change to the scheduler, to schedule next process. Okay? So if you do this way, you got to change schedule next process just a little bit. Because the schedule next process that you've implemented up to date that I gave you out in the notes, that assumes that the running process is not in the ready queue. So when I did this, I altered my schedule next process. And all it is just comparing what I just said, comparing the running process against the priority that the ready queue says. You just have to account for the fact that the ready table may tell you that you already are the highest priority ready process. Okay. There's just some notes about what was that. So, and what you showed right there, that was all of PCPP. All that you do is you set the priority field. So you set the dynamic priority of the running process equal to the ceiling priority of the semaphore. You set the entry of the dynamic processes array at the ceiling priority of the semaphore equal to the running process. Then you insert the running process into the ready queue. Why do we need to insert the running process into the ready queue? If, under the assumption that I've told you that the running process is always in the ready queue, isn't the process running already in the ready queue? He'd have to be already in the ready queue because he's swapped in. He's a running process. If the running process is already in the ready queue, isn't this making the running process be put into the ready queue twice? Yeah, it is. And that's being done explicitly. The reason why is because it's in the ready queue once at its static priority level and a second time at its dynamic priority level. Okay? So the ready queue just has two entries for process running. We don't care that we have two entries because the ready queue, whenever we query it, it just cares about the highest priority ready process. So we just insert the running process at the high priority level, so that way when the scheduler makes decisions, it'll pick out the high priority version of process running and run it. As soon as we reduce the dynamic priority of the process running, we will remove process running at the ceiling priority of the semaphore from the ready queue, and it will remain just at its lower entry in the ready queue. So set the dynamic priority, set the entry in the dynamic processes array, then insert the process into the ready queue at the ceiling, at its new dynamic priority. Okay, so we've got dynamic processes arrays, an array of 64 process pointers, and it is indexed based on dynamic priority. We have the static processes array, which is an array of 64 processes, an array of 64 process pointers indexed by static priority. So the static processes array never changes unless you create a process. The dynamic processes array, its contents can change based on priority elevation. Okay? So this is indexed by dynamic priority. This is indexed by static priority. All right. Okay, as a side note, please make sure you are aware of this, and this comment should also, it's directly relevant to Lab 8 as well. During Lab 8, you've got to determine when you should release a process, okay? How do you determine when it's time to release a process? Well, you've got to keep a counter associated with each process that counts down, is it my release time yet, yes or no? As soon as you get that counter down to 0, then it's time to release the process, and then you release the process, okay? When you are determining whether or not to release processes, you've got to iterate through all the processes in your system. Right now in Lab 8, you only have one 64-entry process array, okay? It's indexed by priority because you only have one type of priority. In Lab 8, there's no distinction between dynamic and static priority. As you transition to Lab 9, the array that you're using right there will be your static process array. You'll create another one for your dynamic process array. When you go through and determine release times for processes, you're going to iterate through the static process array, not the dynamic process array. The reason why is because in a dynamic process array at any given time, when you've elevated the priority of a particular process, that elevated process will appear in the dynamic process array twice. Once at its static priority, once at its dynamic priority. You will also have processes which do not appear in the dynamic process array, and that's because if you've got a process that's masquerading at the ceiling priority of a semaphore, what that implies is that there is another process whose static priority is equal to the dynamic priority indicated by the ceiling priority of the semaphore. Anybody want to say that twice? Okay. You remember the ceiling priority of a semaphore is dictated by who shares the semaphore. So if the ceiling priority of the semaphore is 6, that means there is a process with priority 6, static priority 6, that is going to eventually ask for that semaphore. If you've got process with priority 18 that asks for the semaphore, its dynamic priority will get switched to 6, and its entry in the dynamic processes array, slot 6, will be overwritten. So you'll take the pointer to the process with static priority 6 and overwrite it with a pointer to the process with static priority 18. So the process with static priority 18 will appear once at slot 18 in the dynamic processes array and once at slot 6 in the dynamic processes array. The process with static priority 6 will not appear at that time in the dynamic processes array. It will appear in the static processes array, because in the static processes array, we don't change the entries. We only flip the entries in the dynamic processes array. So when you want to loop through all of your processes, you always loop through the static processes array, not the dynamic processes array, because there's a chance you could have multiple copies of one process and no appearances of another process in your dynamic processes array at any given point in time. Okay. Here's PCP-V. So a process grabs a PCP semaphore, runs, completes its critical section, and it's now time to give up the PCP semaphore, indicating that the process is done with the critical section. So first thing we do is we disable the interrupt. Then what we're going to do is reduce the dynamic priority of the running process back to its static priority. So we say process running arrow priority equals process running arrow static priority. Okay, it's possible, and frequently does occur, that in our previous example where we have process with static priority 18 and process with static priority 6 both competing for the same semaphore. In the circumstance when the running process with static priority 6 asks for the PCP semaphore, we elevate its dynamic priority equal to the ceiling priority of the resource. But by virtue of the fact that that one process, when process 6 asks for the semaphore, its static priority is equal to the ceiling priority of the resource. So therefore, its dynamic priority and its static priority are the same thing. There are situations where this doesn't do anything. We're just setting the dynamic priority equal to the static priority. The process with highest priority to compete for a particular resource, we can refer to that as the ceiling process. So the highest priority that wants the semaphore, that process dictates the ceiling priority for the semaphore. So if process running is the ceiling process, its dynamic priority is already equal to the static priority, and this statement doesn't do anything. Okay? But typically, when you have a lower priority process, it's not the ceiling process relative to this particular semaphore. When it attempts to grab the PCP semaphore, its dynamic priority is usually a higher priority than its static priority. But nevertheless, we reset the dynamic priority of the running process equal to the static priority of the running process. And again, static priority for a process doesn't change. So now that we've reduced the dynamic priority of the running process back to its static priority, we're going to restore the entry in the dynamic processes array at the ceiling priority of the semaphore to what it was before, to the process whose static priority is equal to the ceiling priority of the semaphore. So this is the slot in the dynamic processes array that we overwrote in P. So we overwrote it with whoever's grabbing the semaphore. Now we're going to reset it back to what it was before. What it was before is, so we'll say dynamic processes sub S ceiling priority is equal to static processes sub S ceiling priority. So under normal circumstances, we want the dynamic processes array to be equal to the static processes array, unless a PCP semaphore is held currently by a process. So when the PCP semaphore is not held, what we're going to say is that the dynamic processes array at the slot corresponding to the ceiling priority of the semaphore is equal to, or it points to the same process whose static priority is equal to the ceiling priority of the semaphore. Okay? So the dynamic processes array usually points to the ceiling process of this semaphore at its ceiling priority. But when we go to mess things around, that's when it doesn't point to it. So this is just restoring the slot of the dynamic processes array to what it was before the PCP semaphore was owned. Okay. Now what we have to do is we have to solve a small issue here. Okay. We had this lower priority process that grabbed the PCP semaphore. Its dynamic priority got elevated. And it ran at that higher priority for a little while. And now it's getting lowered back down to its static priority. There's a couple of things that we have to consider. So scenario one, what happens if the ceiling priority, so we know that the process whose static priority is equal to the ceiling priority of the semaphore. So this process whose static priority is 6, that guy, the original high priority guy. So that process, we know, did not want the CPU at the time where the lower priority process asked for the PCP semaphore. The reason why we know that is because the scheduler would have swapped him in and process 18 wouldn't have been running in the first place. Okay? So we now have to ask the question, did that process with the ceiling priority of the semaphore, whose static priority is equal to the ceiling priority of the semaphore, did it become ready while this lower priority process was masquerading at its elevated dynamic level? So if it became ready, we've got to deal with something here. If it did not become ready, we've got to deal with something else. Okay? So this if statement checks to see if the slot in the dynamic processes array with a ceiling priority. So this is the ceiling process of the semaphore. So the process whose static priority is equal to the ceiling priority of the semaphore. If it is currently blocked, what that means, if that ceiling process doesn't currently want the CPU, or it slept through the whole time. So I know it was sleeping when I grabbed the PCP semaphore. If it's still sleeping after I'm giving up the PCP semaphore, I've got to do what's inside here. If it did not, then I'm going to leave things alone because there's a particular fact that I like about this. Okay. If you remember, what we did is we inserted into our table-based scheduler table for our ready queue, we inserted the dynamic priority of the elevated process into the ready queue. So we marked priority 6 as being ready in our table. So static priority 18 got dynamic priority 6, and we put 6 into our ready queue. So that way when the scheduler runs, it'll say, who's the highest priority that's ready? It'll say, well, 6 is ready. And then it'll look up in the dynamic processes array, who is process 6? And it'll grab that pointer and say, this is the guy that needs to be scheduled. It just so happens that during the time where that process owns the PCP semaphore, the process with dynamic priority 6 is the guy with static priority 18. So if it's the case that the process with static priority 6 is blocked, if he slept through the whole thing, did not become ready while this process that owns the PCP semaphore owned it, then what we have to do is make sure that we tell the scheduler this dynamic priority 6 is no longer ready. Otherwise, the scheduler is going to try to run a blocked process. Because what it'll do is if we don't clear the entry from the ready queue, then the scheduler, the next time it runs, it'll ask the ready queue, who's the highest priority ready process? It'll say 6. And it'll go try to run 6. But we've just determined that 6 is blocked. We don't want to context switch to a blocked process. That would be bad. Okay? So if the ceiling process is currently blocked, we need to remove the ceiling priority from the ready table. If the ceiling process is not blocked, what that meant is that the ceiling process was made ready and released and put onto the ready queue during the time that I owned the PCP semaphore. So if it became ready while I owned the PCP semaphore, it did not get to run. The reason why it doesn't get to run is because I'm masquerading as him. I have his priority. He's not even in the dynamic processes array. Whenever the scheduler runs and it says priority 6 is ready, it'll look up in the dynamic processes array at the ceiling priority of this semaphore, and it'll say, well, who's that? Well, it's not the ceiling process, it's process 18, because I've supplanted myself in the dynamic processes array at the right slot. So, if the ceiling process for this semaphore became ready, we just leave the queue alone. We just leave priority 6 as being marked as ready, because that'll allow the ceiling process to run later on. If it's not ready, we clear the queue. We invoke this queue clear function, which just takes the ready queue table, finds this priority in it, and marks it as clear, removes it from the table. So, that's your V. Your V does your backwards P, says lower the dynamic priority of the running process to be its static priority, replace the entry in the dynamic processes array with its corresponding entry in the static processes array. So that will allow the scheduler, when the scheduler says the ceiling process is ready, it'll have the correct pointer to the right ceiling process. And then we just say, if the ceiling process has been marked as ready, we're going to leave the table alone. If it's blocked, then we're going to clear the ceiling priority from the table. Okay. That verbatim is what my PCP semaphore code looks like. Again, it depends on whether or not you're putting the running process in the ready queue and having it sit in the ready queue all the time or not. If you want to do it the other way, and you're confused about how to do it, come and talk to me and I'll help you through it. Okay? Any questions about PCP semaphore implementation? Well, let me rephrase that. Any questions that you're willing to ask right now without going away and thinking about it for a bit? Mitch? Priority Ceiling Protocol, PCP. No, it is not the barbiturate. Isn't PCP a drug you can take? You perhaps will be thinking they're the same thing by the time Lab 8's done, Lab 9's done. Okay? We okay for now? This stuff is break your head stuff. I know that. That's why I gave you out the verbatim implementation that I gave out. I will ask you exam questions on this. You are going to have to understand it. Okay? But you're going to have a whole big fat lab to do to help you understand it. And plus, I'll answer any questions you can cook up. Okay. So the thing that PCP semaphores give you, so number one, you can't not get the PCP semaphore. If you have high enough priority to ask for it, you will get it. Then the other thing that the PCP semaphore does is it gives you mutual exclusion. If you note, the PCP semaphore has no blocked queue, but yet we do account for blocking time. So just because our implementation does not explicitly have a blocked queue, in our response time analysis, we talk about blocking time. Where does a process that is blocked spend its time when it's waiting for the PCP semaphore? It sits on the ready queue. Or, so if a process is blocked, then it's sitting on the ready queue, according to these PCP semaphores. We still account for that time where the process is blocked as blocking time. If a process is sitting on the ready queue and not waiting for a higher priority process, a process who has static priority that's higher than it to run, that's interference time. If a process is waiting on the ready queue because a process with static priority lower than it got elevated to a dynamic priority higher than it, that's blocking time. So again, flipping back to the response time analysis. We account for the time of a process as follows. So the response time, again, is how long it takes for a process to finish the total amount of work it's got. It's got to do the total amount of work it's got to do, which is its compute time. Then we have its interference time, and that's the time where the process resides on the ready queue waiting for all the higher priority processes, all the processes with static priority that are higher than it, to do their work. So this is just when a process with higher priority than you becomes ready, it gets to run. This interference time has nothing to do with semaphores, okay? Anything that causes us grief with respect to semaphores is accounted for in blocking time. So a process whose static priority is higher than mine, they get to run ahead of me because this is a priority scheduler. That's accounted for as interference time. Blocking time is when a process whose static priority is lower than mine somehow magically keeps me from running. And that's just due to the fact that the only time that can happen is when that lower priority process's dynamic priority gets elevated to either equal to or greater than mine. So how we accounted for that in the equations is we defined this B sub I equals max K equals 1 up to cap K usage of K comma I times C sub K. This little k corresponds to a resource index. So you're iterating through all of the PCP semaphores that are assumed to be protecting different critical regions. So considering each critical region in the system. C sub k, we assume that whenever a process grabs a particular critical section or enters a particular critical section, regardless of which process is accessing that critical section, we say that they're all going to take the same amount of time to access that critical section. So this is the time in which we spend accessing a critical region. So the blocking time on process I is equal to the biggest compute time of any resource if that somebody executing that compute time can impact me. Okay? So this usage says whether or not a process, if it can grab resource K, can that cause me to block? So how do we quantify whether or not a process can cause me to block? So if any process grabbing resource K, can that cause process I to block? Yes or no? So this evaluates to a 1 or a 0. If it evaluates to a 1, we consider the blocking time or the total time that the critical section will last for resource K, the C sub K. So all that we do is we just say, okay, find the set of resources which, if they are owned by some process, if that causes me to block, what's the biggest blocking time I'll have to wait? And I'm guaranteed to only have to wait once. So this usage of Ki takes a little bit of getting used to, and it's defined as follows. So usage of Ki is equal to 1 if resource K is used by at least one process with static priority less than I, and at least one process uses resource K with static priority greater than or equal to I's priority. Okay? So this is just a formalization of saying, can a process that grabs a particular resource cause process I to block? It'll cause process I to block if the ceiling priority of the resource is higher than I's priority. The ceiling priority of the ceiling priority of the resource will be higher than I's priority if there's a process that will compete for that resource that has higher priority than I, or equal to I, and a process with lower priority than I will compete for the resource as well. Okay? I'll give you some book problems on that one, and I don't think anybody will really understand what that usage really is and be comfortable with it until you work a couple problems. At least that's how I was with it. Maybe you guys are able to process that a little bit more intuitively than I was. So anyway, response time analysis equation. I showed this one at the last time of class. You've already seen this first part of it where the response time is the sum of the compute time and the interference time and the block time. Okay? So what this does, this gives us mathematical equations that govern the behavior of a system. So we can boil down a proof of schedulability to a math problem. Math problems work really well for final exams. So I'm going to give you a few of them to practice on. Okay? Yeah, so response time analysis questions make great final exam questions. All right. We good with PCP for the time being? So you're going to have to understand what is the PCP semaphore, what's its purpose, what's this whole dynamic process and static process and dynamic priorities and priority inheritance and priority inversion, what's the problem that PCP semaphores are intended to solve, how do you model that mathematically, and how do you solve the equation to prove whether or not a set of processes are schedulable. So Lab 9 is going to ask you to implement PCP semaphores, and the response time analysis in C, running on the TS7200. That's phase 1. Now let's talk about the hard part, which is phase 2. Okay. So Lab 9 has 2 parts. Number 1, you're going to implement and test PCP semaphores. You're going to add some commands to the set of commands that I've asked you to implement for Lab 8. The set of commands will be to create a new kind of process and to create a PCP semaphore and to allow these new kinds of processes to share PCP semaphores, basically to set up a similar infrastructure that will support PCP semaphores similar to what you had for Lab 8. Okay? So, and then the other thing is just don't break anything. Make sure all your Lab 8 stuff still works. Okay? Number 2, implement a software UART. So what we're going to do is discuss what UART is. Anybody know what UART stands for? Besides Mitch. Know it all. Okay, Mitch, fine.
Universal asynchronous receiver.
Universal asynchronous receive and transmit, or various variants of the grammar. But anyway, so the whole idea is we're going to, you know how you can hook up your serial port to your board, and you can use printf, and printf sends the data out, and you can use your fgets and get data back and forth, so you can have data transmitted back and forth between the board. We're going to just basically do that same thing, except for we're going to use the digital I/O pins of the TS7200 board to do it. There are hardware chips on the board right now that facilitate getting in each individual bit from the serial port and collecting that into a byte, and then all that we have to do is just go out and call the functions which grab that byte that's sitting in a memory mapped register. That's what the code down at the bottom of write.c did, and the code that's in, or not write.c, inside the syscalls.c. So you remember when I had to trace down printf down to where the point where it talked to the serial port? So we just have a couple of status registers we query. We have a status register we query, and then we grab data off of a data register. Well, part of that data register, this is a serial port. So what that means is data comes in serially, or 1 bit at a time. So you've got bits coming in, and hardware already on the TS7200 board is responsible for collecting those bits and creating an 8-bit word out of them and making sure that data is framed properly and all that. So what we're going to do is do all of that, what that hardware does. We're going to do it in software. And it's going to require lots of fun concurrency and use of interrupts. And anyway, it's going to be very painful. You're going to learn a ton. Okay. I don't give you anything that is not painful in this class. Okay, so what we're going to do first, in order to do a software UART, you have to understand the RS-232 protocol. Okay? This is really simple there's not really all that much complicated about the RS-232. All that we just think about, we have a sender, we have a receiver, and we have a wire that connects them. Okay, so this one wire is able to carry an electrical signal. You can't send 8 bits in parallel over one wire. Computer engineers sometimes get a little bit confused about that one. Wait a minute, I've got a wire, why can't I send? Oh yeah, it's electricity. You can't drive a pin both low and high at the same time. Okay, so effectively this is just, we're communicating data from a sender to a receiver. We've got an electrical connection between the two of them, and we've got to send bits over the wire. Okay, so we have to send 1 bit at a time on the wire. The bit will either be at a high level or a low level, and then the receiver has to determine whether or not it's getting a high or a low. Synchronization occurs. So how do you know when you're sending data and when you're not sending data? So how do you know if you're just sending a bunch of lows, or if you're just leaving it low until you're ready to send some more data? Well, we have to frame the data that we send and do synchronization. We have to have some sort of handshaking between the sender and the receiver. So the sender has to kind of say to the receiver, hey, I'm ready to send some data, and then maybe the receiver will send back to the sender, okay, go ahead. And then the sender starts sending the data. Well, how much data is the sender sending? Does the receiver know? Maybe the receiver can first, or maybe the sender can first send over a little packet that says, by the way, I'm going to send you a byte. I'm going to send you 10 bits. I'm going to send you 12 bits. So you can have different levels of synchronization there. The level of synchronization is specified and predetermined with RS-232. It's configurable, and you configure the sender and you can configure the receiver, but the whole point is before you start any transmissions, you set up the receiver and the transmitter, the sender, to both agree on the format of the data that you're sending. Okay? So the format that we're going to be using for Lab 9 is the following. We define a frame as a start bit, and then 8 data bits, and then a stop bit. RS-232 also provides for, you can have more than one stop bit. You can actually have a bit and a half of stop bits if you want to. You can have a parity bit in there as well for doing error checking. But we're doing, this is called 8N1, where we're having 8 data bits. You always have one start bit, and then you have one stop bit and no parity. 8 data bits, N, no parity, 1 stop bit. Okay? So we configure both the sender and the receiver to say, okay, we're doing 8N1. Okay? Then how often does the data come over? Well, you're going to, when you're sending a bit, how long you're going to assert that line for a particular amount of time. How long do you leave the line low when you're trying to send a low? Do you have to always have all the bits being sent for the same amount of time? And the answer is yeah. So this is what we call baud rate, the time that we leave the line asserted in order to transmit a particular bit. Okay? Time per transmitted bit. So 200 baud, what that means is we transmit each bit, we hold each bit on the line for 1/200 seconds. Okay? This is different than the data rate. This is just saying how many bits do we transmit each bit. And again, you remember, over here with 8N1, in order to send 8 data bits, you have to send a start bit and a stop bit in addition to the 8 data bits. So you transmit 10 bits for every 8 data bits you want to send. What this means is you have some overhead in order to transmit the data. So if you're measuring the aggregate time it takes to send a kilobyte from here to there, you take your baud rate and you have to factor in for every 8 data bits of this kilobyte you're trying to send, I'm also sending 2 bits of overhead. So this is what it looks like. When you're going to transmit, if you put a scope on that wire and look at what's going on the wire, we have a start bit that initially gets sent. That's at the logical value 0, and the stop bit is at logical 1. And I'll tell you what the actual voltage levels for these guys are in a minute. Okay? So we wait for some time. The line floats at a logic 1 level, and then as soon as this transmitter is ready to transmit, it sends a logic value 0 and holds it there for 1 bit period. So starting at this point, we wait for 1 bit period while driving that line low. So that's our start bit. And then the next bit period, we send D0. D0 is the first data bit. Is that D0 a 1 or a 0? Well, it depends on what the data is that you're transmitting. It could be a 1 or a 0, but the point is we send the first bit and we hold that on the line for 1 bit period. Then we send the second bit, hold it on the line for a bit period, and so forth. Then we send D7, we hold that on the line for 1 bit period. As soon as we're done with D7, then we hold the line high for at least 1 bit period, and that is our stop bit. Okay? If we're only sending 1 byte, then all that we do is we just leave the stop bit going. If we want to send another byte right after it, after we hold the stop bit for 1 bit period, we assert a start bit again, hold that for 1 bit period, and do it again. Okay? So this is the guts of RS-232. You send a logic 0, then 8 data bits, then a logic 1 for your stop bit, then a logic 0, 8 data bits, logic 1. Yeah?
The receiver's going to be checking for 8 data bits, right? And then it's going to be checking for the stop bit.
So the receiver, what it's going to do is, so this is what the transmitter does. As soon as the receiver, it's going to be sitting here polling the line, the wire, and it's going to say, okay, did I receive a start bit yet? Did I receive a start bit yet? As soon as it sees a start bit, it says, okay, that start bit should be there for 1 bit period. And as soon as it's done with 1 bit period, then I look for the 8 data bits, 1 bit period at a time, and it'll sample those guys and collect each of those guys, put them into a shift register, and then it'll make sure that the stop bit gets received. If the stop bit is not received, if you get the 8th data bit and you get a low right here, that's called a framing error. And so then you'll have to resend. Yeah, you discard what you have. So then, but under the assumption you don't have a framing error, You just end up with a stop bit. The receiver looks for the stop bit and will say, okay, yeah, there's a stop bit there. And then it has to be immediately, as soon as that stop bit's done, you have to immediately be able to reset yourself and go for another start bit. Okay? Denise?
So it's always going to start at 1, like
Okay, so the question is, will it always be at logical 1? That depends on if you've got your board configured to be a transmitter. If your board is only receiving, it's not going to drive any pin anywhere. But your PC, if it has a serial port, will always be driving one of its pins at the logic 1 because it's always sending a stop bit, and it's intended that that's going to be somebody you're transmitting to. Okay, the other thing that with serial ports is that we support full duplex connections. So we actually have one wire for sending from sender to receiver, or from computer A to computer B, and then you have another wire that's for sending from computer B to computer A. And both of them in parallel run these start bit, 8 data bits, stop bits, transmitting independent of each other. So you can have full duplex connections. Okay. The other thing that I wanted to point out to you before I'll let you go here. So you've got the bit period, that's equal to 1 over the baud rate. These are your data bits, your voltage levels. RS-232 inverts, okay? So logic level 0 is a positive voltage. Logic level 1 is a negative voltage. Any voltage between 3 volts and 15 volts will work as a logic 0. Any voltage between -3 and -15 will work as a logic 1, okay? So logic 1 is actually a negative voltage. So if you cut your serial wire right in half and you put your scope on it, when you look for your stop bit, so when you look for your stop bit right there, if you've got the transmitter, you should be seeing the stop bit driving something to logic 1, which is a negative voltage, somewhere around -10. Okay, in order to do this lab, you're going to need to get a level shifter chip and 4 capacitors from Heidi. It'll be about $5. Okay, she knows what the level shifter chip is, and when I give you out Lab 9, I'll give you the data sheet for that. But you're going to need to purchase a level shifter chip, which will convert the voltage levels of the DIO pins, which is 0 to 3.3, to the logic levels of RS-232. It'll handle both the receive side and the send side. So you're going to need to have a breadboard for this Lab 9 for phase 2. Okay. More about RS-232 and Lab 9 next time.